Let's just add a little bit more details. There are not a very robust definition of onset and completion, but we have seen this before in terms of the transition. We said the warm core cyclones, tropical cyclones, have, of course, a warm core, and the strongest winds are in the lower part of the cyclone near the surface, and the top at the outflow actually winds get weaker. The vortex is much more stable near the surface. Stability drops off, and you can see the structure here, and it's much more symmetric with the strongest winds in the inside, and then winds weaken as we go outside with these feeder bands feeding in. Whereas the extratropical cyclone has a remarkably different structure with weaker winds near the surface, a cold core that is asymmetric and tilting, and has strongest winds at the upper levels. And these asymmetries typically are a combination of the cold and warm fronts, and then there are occlusions and wrapping around of the fronts and so on. And typically you get large-scale gale force winds on the southern side with lots of rain, snow, and ice and snow on the northern side. So it's this transition from this warm core symmetric structure to this non-asymmetric structure with the tilt that defines the onset. Completion is, some people argue for a re-intensification, but that's not always agreed upon by everybody else. So obviously these are not strict, as I said before. So as the tropical cyclone moves into the colder waters and meets the mid-latitude trough, which is basically the southern migration of the jet stream, there are interactions which can allow the cyclone to survive or smother it and kill it. And here is just a schematic of a cyclone here with its counterclockwise flow, and there is the front and forming a mid-latitude cyclone, just as example. But if you look at the structure, you get cold and warm fronts combining, and depending on how strong they are and how the occlusion goes, the fronts can get wrapped around each other. And the mid-latitude trough, as we said, upper level trough is here. So the jet stream, I think all of us know what that is. The vertical shear is very strong. The strongest winds are in the upper troposphere, and the especially during the winter months there are a lot of migrations, meridional meanders, let's say, of the jet stream, and it has a ridge as it upper level ridge as it goes northward. So there is the cold Arctic air and the warm subtropical air, and the jet stream can be thought of as a referee in between. So there is a trough as it migrates south, so you have convergence coming in here, divergence going out here. So obviously it's important because the jet stream is able to put down weather on the surface. So this is the surface map, and here you have warmer air, milky skies, kind of a strange descriptor, but there we are. So you have a cold front here, and clouds increase, warm air is intruding into higher latitude, so we are going northward here. And there's high pressure here and low pressure on this side. So there is winter snow, clearing skies, rising pressure, and showers on this side, and the movement of the front is towards this. So there is low pressure rising air into the diverging upper ridge over here. So you can see that there is falling pressure, precipitation on this side, and clouds thickening with cirrus clouds at the northern end of the system. I'm just showing this because this is typical typology of what we expect as the tropical cyclone, if it survives to these latitudes, how it's going to interact with the mid-latitude trough. Okay, that's going to become a key ingredient for the onset and completion of the extratropical cyclone, cold core cyclone, as we called it before. And we have seen these cyclone phase space diagrams showing here the storm relative thickness symmetry, so 900 to 600 hectopascal symmetric and asymmetric front. So here is the cyclone going from A transitioning into a extratropical cyclone, and we saw the analysis and forecast, which we won't bother about, but look at the intensities dropping all the way down to 950 here, and the mean radius of the 925 hectopascal gale winds with these winds and the size of the region that is covered. So you can see the transition going from symmetric warm core. It started actually as a subtropical storm, I think, beyond the tropics, I don't know. At least started as a symmetric cold core, and then became symmetric warm core, became asymmetric warm core, and ended up being asymmetric cold core. So this diagram is much more descriptive and mechanistic in terms of its transitions. And the other part of this, so we are looking here at the thermal winds in the lower level, 900 to 600 hectopascal, whereas here we are looking at the relative thickness of the layer. And the other part of this diagram, of course, was the lower level thermal winds and the upper level thermal winds, 600 to 300 hectopascal. So that also gives you the much better information for the cold core cyclone, because the winds are much stronger in the upper level for a cold core extratropical cyclone. So here you are now going from the initial cold core symmetric structure to deep warm core, shallow warm core, and then deep cold core, again showing intensities in hectopascal and mean radius of the 925 hectopascal gale force wind. So you get the sense that whatever survives to that those latitudes is going to interact with the mid-latitude trough, and then have these transitions to a cold core asymmetric front that is tilted to the northwest. You can read up more details and even find some better figures on the web, including some animations, but I'm going to leave it at this, and then we will look at some mechanisms in the next podcast for extratropical transition. Okay?